Hello and welcome to one of the last Pint of Science events from 2021. My name is Chris Snowden. I'm a science communicator and public engagementer. Yeah, we'll go with that. And I'll be your host for this event. I'm from the Leeds team, and tonight's event is Science with a capital S. We have four fantastic speakers for you this evening, joining us to talk all about science. It has a huge influence on our lives, and particularly over the last year or so, we've heard a lot about following the science. But what does that mean? What is science? How is it done? Who does that science? And then where do scientists consume their science compared to, well, all the rest of us? Usually, of course, Pint of Science would be taking place in the pub with a pint, but with present circumstances, things are a little different this year. I do still have my pints for the evening, but I am in my slightly less glamorous spare room at home. Before we kick off and I hand over to our speakers, as we are online and you can join us from anywhere, it would be great to know where you have joined us from. You can pop this in the YouTube comments just next to the stream. There is a very short delay, so I might be a little slow responding, but I will respond, I promise. And we have had a few people. It mostly seems to be Yorkshire tonight. We've had Sheffield, Hull and Leeds so far, but it would be good to know if we've got people beyond the bounds of Yorkshire as well. That would be lovely to know. For our session this evening, the way it's going to work is we're going to hear from all four of our speakers, one after another, once I hand over to the first in a moment. And then once we have heard from all of them, we're going to open the floor out to you for questions as a panel discussion. So if you do have questions as we go, you can ask them in the YouTube comments throughout the talks, or you can save them all up until we move into the panel discussion after all four of the speakers have been, and well, you see this face again. And we do have plenty of time for the panel discussion, so please do ask away with your questions, and we will try to get to as many as possible. I'm seeing now we've got Nottingham, Hull, Edinburgh, London, Birmingham, Arran, Glasgow, Cork, yes, it's out of the UK. This is brilliant. This is what we like to see. The great thing about doing it on the internet. It sounds like it's raining a lot in Hull. I think it's just starting a little bit outside my window here in Leeds. Before I do hand over to our speakers, although I said I want you to ask us questions, I do actually have a question for you as well. And it's in preparation for the third of our talks this evening. So I want you to put your thinking caps on. You don't have to answer straight away. You do have a couple of talks to think about it. But I want you to pop into the YouTube comments. What do you think some of the characteristics of a scientist are? So have a think. What do you think, to you, some of the good characteristics of a scientist are? You've got plenty of time, so don't worry. You can have a good think. But I'm not going to prattle on for ages because we have four fantastic speakers, so you want to hear from those. So without any further ado, I am going to hand over to the first of our speakers this evening, which is Ben Hanson, who is... went the wrong way again. Ben Hanson. So I will disappear and hand you over to Ben.
Thanks, Chris. Hi, everyone on the internet. Welcome to Science with a capital S. I'm going to be giving you the introduction to what the scientific method is today. Like Chris said, I'd rather we all be in public, but here I am as a classic scientist with a pint of coffee at 8 p.m. on a Thursday evening. So maybe that'll be one of the characteristics of a scientist that you'll all put. But yeah, I'm going to be introducing you all to the scientific method. So without further ado, let's get started with that. Okay, there we go. So a little bit about me first. I'm Dr. Ben Hanson. My field is computational biophysics. So that's a bit of a mouthful, right? But really, I just use computers to study the physics that happens in biological systems, right? You ram it all together in one phrase, computational biophysics. So the sort of things I'm interested in are biological mechanics, gels, molecular motors, and crazy abstract maths. I'll try and avoid most of that tonight. There might be a little bit. But the reason I'm here is because my other interests are the philosophy of science, science communication, and the perception of science, so how we all view science. So I'm going to give you a little bit of an introduction into what I do as a scientist, and then we'll go into the scientific method from there. But there's some social media stuff there. That's my Twitter handle. We've also got Pint of Science, hashtag Pint21. Get involved in social media. If I say anything particularly controversial, they'll be free to let me know. So the start of all biophysics is this idea of a protein. So what is a protein? If I ask you guys at home what you guys think proteins are, what comes to mind first? I wonder, is it maybe this, protein powder? Perhaps it's this, the result of protein, right? Extremely muscular people. But to me, as a biophysicist, this is more what a protein looks like. So here on the left-hand side, we've got something called I-27. On the right, protein L. I'm not going to get into what they are, but the difference between them, you might be able to tell, is their shapes. On the left, we've got this sort of ribbony shape. Those are called beta sheets. And on the right, we've got a little bit of that too, but we've also got this spring-like thing. That's called an alpha helix. But because I'm a physicist, I can take these structures and I can make them move. So that's the physics part of all this stuff. And you might be able to see that different shapes move in different ways. Little bits at the end might move more. They sort of retain their overall shape. So to us biophysics people, this is what a protein looks like, this sort of shape. But I am a physicist, so this sort of level of detail, a bit too much for me. I kind of want to make everything into a sphere. But importantly, it's a sphere with these things on the surface that allows them to stick together. So if I let them stick together, and this idea of steric means that they can't move past one another, I can stick 10 together in a row and start them going, and you get this sort of different flexible behavior. So that's just what you get from sticking spheres together at the surface. But I might not want to stick them together at the start. I might want to stick them together over time. And in that case, you get these beautiful network structures. So this is a representation of something called a biological network, perhaps a protein hydrogel, perhaps not. We'll see in the future. But my simulations are a lot bigger than this. They look something more like this. So if you just allow spheres to stick together over time, with the laws of physics, you get these beautiful network structures emerging. So the idea there is simple models generate complexity, and simple models help us to predict complex reality. So that's sort of the theory. That's the bottom-up stuff. We start with spheres, let them stick together, and they form these beautiful structures. There's some of the crazy maths. We'll get rid of that. But we've got this idea of maths. We've got this idea of prediction. We've got this idea of deduction. This is the bottom-up stuff. But a lot of science is experiment. In fact, a lot of people would say that this is the core of science, is experiment. So we get this thing that's 100,000 times bigger, and we put it inside this machine. This is called a rheometer, and that allows us to take a biological network, a sort of material, and stretch it and apply forces to it and move it and twist it and see how it responds at sort of this length scale, the human length scale. And then we've got this idea of data, analysis. The philosophy word for this sort of stuff is empiricism. But then the real question is, what's going on in the middle? How do I get from the bottom to the top? How do I get from the top to the bottom? This is the real question of what science is. So moving on from proteins, we've got the scientific method. So keep that sort of model in your mind, and we'll go through the scientific method. So the first thing you do, and we learn this at school, is you make an observation. From there, you collect evidence. From there, you analyze that evidence. And from there, you develop a theory. So observe, collect evidence, analyze, develop theory. If you were to watch society at work, you might think you stopped there. And from there, once you've got this theory, you can develop anything you want. Technology is the output of science. But I wonder over the next 20 minutes if we might change that opinion, because for me and other scientists, and you might be able to tell, this is more of a cycle. And that cycle continues. You observe, you collect evidence, you analyze the evidence, you develop a theory. You continue doing that, your theories get better, your evidence gets better, and eventually knowledge is what emerges from there, moving through this cycle again and again and again, with technology being more of a byproduct. So that's a quote from one of my favorite fantasy authors, Brandon Sanderson. He says, "Journey before destination." Now, he's talking about high fantasy stuff there, but he's saying something about science as well. The idea that science is the process and not the solution. This cycle allows us to reduce uncertainty, and that is super important in the modern world. I mean, you can start anywhere on this cycle, and it never stops. So my question to you guys is, what on earth are scientists, economists, politicians, faith leaders, philosophers, Brian Cox, I might have added David Attenborough, and friends and family really talking about when they use the word science? Tell us in the Twitter and YouTube comments, do you guys ever encounter the scientific method yourselves outside the lab or in the lab if you're scientists? When Boris Johnson, and feel free to tag Boris Johnson in this, by the way. When Boris Johnson tells us he's following the science, which he regularly does these days, do you think he understands what he's saying? I wonder. But without any more from me, I'm going to hand over to the first of our Alexes, who's going to tell us a bit about what science is rather than how it's done.
Thank you very much, Ben. Right, yeah, so I just get started on it, yeah. So I framed this idea of what the science is around this question if science is a verb or a noun. And if that doesn't make complete sense to you right now, I hope in 5 minutes it will. But to start off, I'm just going to give you a quick introduction. This is me. I'm a scientist at the University of Leeds, and I work in the genetics of crops like wheat, which is what you see on the left here. And a lot of my work involves hydroponics, which is what this system on the right is. But I'm not here to talk about that today. I'm here to talk about what science is, and I want you to start thinking about it with this question: how concrete is scientific fact? How concrete do you think it is? And it's not a trick question. I'm hoping for most of you, the answer is pretty concrete. There's a reason, right, why scientific fact sounds a bit more definite, a bit more sure than regular fact. There's a reason why a newspaper might tell us that scientists say something rather than just people say something. There is a reason, because generally scientific fact is a fairly concrete thing, or we feel like it is. But at the same time, we know, at least to some degree, that it's not completely unchanging. For example, some of you might recognize this fella here. Those of you who don't are probably thinking maybe it's a moon, maybe it's a planet. Well, if you thought that second one, I'm afraid you're wrong, because this is Pluto. And a few of you might remember a couple of years ago that scientists got together and decided Pluto isn't a planet anymore. I was taught at school, and I imagine almost all of you at home were taught at school, that there's 9 planets in the solar system, and Pluto's the 9th one, until a few years ago when it just stopped being. The reason I tell you this is because I want you to understand that we're not talking here about conspiracy theories or fake news. We're talking about genuine scientific fact and when it changes and why it changes. And to understand that, I think we need to go back to this process of science that Ben introduced us to. This is a more simplified version, but it's still the basic idea. You come up with a hypothesis from an observation, you experiment to test it, and you analyze those results. And yes, if you were paying attention to Ben's talk, you know that in the real world, this doesn't end there, and in fact cycles around again and again. And so it's easy looking at this cycle to think that the way it must work is that it cycles around again and again and again and again, getting closer and closer to fact, to a concrete, definite, 100% infallible fact. And this isn't quite the case. The reason for this is that, despite what some people think, science is not completely obsessed with fact. In fact, really, the ultimate focus of science is data. It's interpreting data and collecting data. And it depends on the type of scientist you are. For me, that data might be the fruits or branches that a tree produces or a plant produces. For someone like Ben, that data is how proteins move. For a completely different type of scientist, that data is how children learn how to write. But it's all still data. And that's the ultimate focus of any modern scientist. And so when we look at science in this data-focused way, we can then sort of start to get an idea of at least when the science changes. It kind of makes sense that really either we come up with new data that changes what we think, or somebody comes up with a new interpretation of the data we already have. And so to give you an example, because I'm a geneticist, I'm now going to give you a 60-second crash course history of genetics. So starting about 160 years ago with a man whose name hopefully you almost all recognise, is Charles Darwin with his basic theory of evolution. And a few years after that, a German monk called Gregor Mendel came up with this idea that genes were passed from generation to generation. But then sort of for quite a while, genetics sort of fell out of fashion and a lot of work wasn't done on it for quite a while, until sort of the 20th century, when it started picking up steam again. And fairly close together, we get a series of very important discoveries that genes are stored on these things called chromosomes. And then a few decades later, that what genes do, which is their sort of recipe for proteins. And then a few years after that, genes are made of something called DNA. Although in 1944 at this point, still not understanding what DNA really was. Until eventually in the 1950s, when we really made this groundbreaking discovery that had a huge impact on biology, chemistry, health, that DNA is this double helix structure, which was so important that I'm betting that even if you at home before tonight knew nothing about genetics, you recognize this symbol on the left as a general image that brought to your mind words like genetics or DNA. And this history sort of backs up a few of the points I've just made. So firstly, it's very clear that this is not a history of us getting closer and closer to a fact or to truth. Charles Darwin was completely right already in 1850, at least about what he said. He wasn't right about chromosomes and proteins and DNA, but he wasn't wrong either, because he didn't even know they existed. No one in the 1800s did. This isn't a history of getting more and more correct. It's a history of understanding all the things that we didn't even know we didn't know. Another point that this sort of proves, using the DNA double helix example, is this thing about data changing the science. So for example, with the double helix, Rosalind Franklin, she was a scientist who worked, her experiments involved firing X-rays at molecules and making pictures off that. This picture next to her on the right, believe it or not, is a picture of DNA. She came up with new data. Watson and Crick, meanwhile, names you might recognize, took this data, took these images, as well as the data from lots of other scientists working in different fields, put it all together and interpreted it to mean that DNA must be a double helix structure. And so looking at science in this way now, we can sort of come back to this process and see that in the real world, it's less of this iterative change, getting closer and closer to fact, but it's still an iterative change, but it's more just slowly changing, just different, understanding different things in a different way, perhaps even things we didn't even realize we didn't know when we started. And that's why I've tried to sum up this idea with this question of science being much more like a verb than a noun. We use science as a noun, but that sort of implies that it's static and it's unchanging, which is quite unhelpful, really. It's much more like a verb, a doing word. It's constantly moving, it's constantly changing. And not just in this way of constantly upwards, but outwards is a better description of how it changes. It's constantly pushing out and exploring and changing and reevaluating over time. And if you come away from this talk with one idea in your head tonight, I think that's the one I'd like it to be, which is why I've made this the final slide, where I've tried to sum it up with these images. But I think we've heard enough now about what science is. So Alex is going to talk to you about who's doing science, or at least who's doing science in the 21st century right now. So take it away, Alex.
Hey, thanks for that, Alex. Alex first. So building upon what's already been said, I'm going to talk a little bit more about who decides what is researched and the implications of this. So first, just a little bit about myself and my research. So I'm a first year economics PhD student at the University of Leeds. I've had a bit of a checkered history. So after my undergraduate degree, I worked in the charity sector and the expeditions industry for a while before becoming really interested in the question of how we create a more sustainable economy, such as the one envisioned in Kate Raworth's Donut. And that led me on to my research question, my project at the moment, investigating climate finance justice. But enough about me. On with the presentation. So with the COVID-19 pandemic, there's been a lot of mention in the media and by politicians about this idea of listening to the science. but if we're listening to the science, who are we listening to? Who is involved in this conversation? So for me, more importantly than considering who is involved in the conversation is who is excluded, who isn't involved in this conversation. And the following slides consider this at the level of the scientist, the level of the individual. So first, let's consider this idea of Homo scientifico. So this is the idealized version of a scientist. So if you could build a Frankenstein-like scientist from scratch, what this ideal scientist would look like. So Chris asked you guys at the beginning to feedback what characteristics you thought a scientist should exhibit. And thank you for all of you guys who did respond. I particularly liked Phil's comment about crazy hair, definitely a very essential part of being a scientist. Interestingly, no one mentioned what I assumed was a key characteristic, which is this idea of objectivity. So going back to Ben's talk about the scientific method and this idea of observing and collecting evidence, the scientist is always on the outside of that. They're always impartial and recording the data rather than being involved in what happens. So is this reflective of reality? Are scientists actually objective? So I would argue no, although the scientific method can be objective, the scientists conducting these experiments and investigations aren't. So while the goal of science may be to determine truth, it's the scientists themselves that subjectively decide what research questions they're going to ask, so how they orientate their research. And these questions, to a certain extent, are shaped by these individuals' backgrounds and life experiences, as well as more structural features such as the scientific community that they're part of. So does this matter? Maybe. Academia is not particularly diverse. Recent research by the Royal Academy of Science has shown that there are many more white, and I'd hazard male professors and academics than there are of other ethnicities. So now, while I'm not trying to say there's anything wrong with being a white male professor or academic, I'm saying having a homogeneous group of researchers means that the perspectives from which research questions are being generated all come from the same sort of points, maybe. And that means that scientists are consequentially less likely to challenge, as they may not be aware of embedded inequalities. So something to consider. In conclusion, I would just like to say that science is not objective because scientists themselves are not objective. And knowledge generation is explicitly shaped by scientists themselves, as well as by their supervisors and the scientific community that they're part of. And I think it's really important that the scientific community critically assesses the power dynamics underpinning this and try and identify opportunities for transformation. So we can ensure that the most innovative research, most innovative and contextually specific research that is suitable for these times is being generated. Okay, so that's enough of me. If you have any questions, please just post them in the comments. And now I'll hand over to Izzy.
Cool, thanks Alex. Hi everyone, I'm Izzy, and now that we have talked about who is doing the science, I'm going to have a quick look at where that science goes once it's done and how we as people who haven't done that research can actually access it. So therefore, we'll be talking about a sense of science. First of all, a bit about me. I am a first year PhD student in the School of Geography, again at the University of Leeds. My research focuses on greenhouse gas emissions from agricultural soils, depending on different management practices that are used. And this is really important in terms of climate change and reaching organisational targets like net zero. So let's talk about how we absorb science. The first example here being scientific journals and papers, and you might not necessarily know what these are if you're not from a scientific background. They are essentially themed publications that will contain a handful of papers, so these might be single studies, maybe talking about an experiment that's been done, or a review of several studies that have already been published. And they are very formalised in the sense that they will have a set structure, so they'll contain an abstract or a summary, a background of the research, an in-depth look at the methods like Ben discussed, and summarising the results and explaining those. And because of this, they're very specialised, very academic, very formal, and they can be therefore really inaccessible to those outside of the academic community. They are made for researchers by researchers, and if you're a researcher like me who reads these every single day, they're really useful, but they might not necessarily be the best way of absorbing your science if you don't have access to them. Here's another quick look at one called Agriculture, Ecosystems and Environment. You can see that there have been 247 volumes of just this one publication, so there's so many out there, and a handful of the papers that it might contain. Now let's look at something that you might be a bit more familiar with. We've got an example here of the BBC News online news page, and this is something that you might come across way more in everyday life. So these will be made for the public to tell them often about scientific research in a way that they might not necessarily realise is scientific research. So the one here to the left is a bit more obvious, from December last year, about one of the COVID vaccines being judged safe for use. And you can really see that the main reason for these being produced is to get the research out there, but it's research that's applicable to you in your everyday life, so you're going to be interested in it. And because of that, the reading and the language is going to be really accessible, less detailed, and will just mean that it's a really easy and quick way for you to absorb your science. It is really important, however, as with anything online, to be wary of the source. Not every organisation or publisher is going to have the same high standards, and they might not necessarily back up their claims with actual science, so it is important to be cautious. Another way of perhaps diluting that scientific research is social media, and unless you are a scientist, you might not think that science is that prevalent on social media. However, there are lots of pockets of scientific communities in really specialised fields. So there's a few tweets here which are specialised to my field, so they're all about soil and crops. However, you can see that because of the limited tweet character allowance that you have on tweets, there's kind of a summary of the paper that the person then goes on to provide a link to, or an article. So you can kind of get a summary from their tweet, which is a diluted version of the research, and then it offers you a gateway to then explore that a bit more. It's really important to consider that social media is really great for science. It's a great way of sharing your research and getting it out there, and also making new connections. But again, like the online articles, be wary of your source, because not everything you read is going to be scientific fact or necessarily from a scientist, even if it seems like it. Again, on social media, you can consider that it's really important for science communication, and this is a really exciting thing to be involved with. We're kind of doing science communication right now. We're talking to you about science. So science communication is basically about making science fun and accessible to everyone. It doesn't matter on your educational background. It just matters that you're having a really great time absorbing science. I could talk about this for a week's worth of talks, so I won't go into it anymore now. But if you are interested in getting into science a bit more, then social media is a really great way to do so and discover what you're interested in. Finally, a quick example from my study area, which is a little bit different. So these are two screenshots from a website called Ag Evidence, which have been created by the Nature Conservancy. And basically, this website collates all of the results and all of the findings and data from papers that kind of fit the criteria it's interested in, and it puts those findings into interactive charts and graphs So people like farmers and policymakers can click on it and explore the data in a way that's really accessible and practical for them, and it doesn't rely on them reading a journal article that they might not necessarily understand or might not even have access to. So it's a really nice example of how you don't have to read paragraphs and paragraphs to absorb science. There are other ways. Think of podcasts, documentaries, watching it on the TV. There are so many other ways. So hopefully you've enjoyed this little snippet. Let us know in the comments how you interact with science. Do you even realise that you're interacting with science when you're doing it? And do you take any precautions when absorbing science from different formats? Thanks for listening, and I'll pass back to Chris.
Thank you very much, Izzy, and to all of our speakers. So Ben and both of the Alexes, which is not confusing at all for the upcoming panel discussion. So yeah, that was a really, really great summary of, or at least a very quick overview of the how, the what, the who, and the where of science. And I am biased, but I particularly enjoyed Izzy mentioning the science communicators as being important. So yeah, I'm going to welcome all of them back in a moment. But yeah, if you have got questions, do pop them in the comments. I know we've had one or two already. I have my own question or questions for them anyway. But yeah, do feel free to stick them in. I am also keeping half an eye on Twitter as well. So particularly thank you to you, Karen, for that spectacularly timed photo you've put up of me gesturing towards Ben with pulling a very strange face. I'm not quite sure why I'm looking like that, but anyway. So yeah, so I think we might as well get everyone back now, so we can get Ben back, and we'll refer to the Alex on the right as that Alex as Al, and then the Alex below me as Alex to save my own sanity, so I can remember which one is which. So yeah, so if you do have questions, do feel free to stick them in the chat. I am going to kick us off with one of my own because I think it's quite an interesting thing and something that I find really fascinating as someone who loves science and talks a lot about science, but doesn't actually do science day to day at all. That's not my area, which I'm going to throw out to all of them. But the first question, that is my personal one. I'm the host. I'm going first. Is have you experienced any times when the science has changed for you? Like the theory is different, or things have actively changed. And given I think it was the foundation of both of those, we'll go. Let's go to Al first. What is there any times you've kind of experienced this or seen this beyond the obvious examples of things like Pluto?
Well, I mean, I would argue that for any good scientist, it should be changing in small ways all the time. Because if it's not, then you're meant to be, as a scientist, discovering new things. If you're never changing our understanding, then you're just doing stuff people have already done. As a specific example, I think for genetics, like the big one is this idea of epigenetics. If you did A levels, or if you went to university and studied biology, and if you're about over the age of 30, you will have been taught that there's two things that affect your traits: your genetics or your environment, and that's it. But then we sort of now have this understanding of this concept of epigenetics, which is kind of like a weird middleman where other little things can change that's not related to either and is sometimes related to both. And I think that's a perfect example that genetics used to be this really clear-cut thing of everything is either genes or environment. And the more and more we learn, the more we realize that's just not the case. And we just didn't have the tools, we didn't have the data to understand how wrong we were.
Mm-hmm. No, that's a very, very good example. So Ben as well, the same question.
Yeah, actually, the science I sort of do is always really quite niche. So I don't want to get too deep into the technicalities of it, but the models that I use, the mathematical models, they are changing in my research all the time, because that's about how you use maths to interpret data, right? So if you watch The Big Bang Theory, they talk about this in terms of loop quantum gravity and string theory, and they make a big joke out of it, but it's a serious thing, right? You can use different types of maths to describe the same data that you're getting, and that happens to me on an almost daily basis. But another thing that I kind of want to say is sort of around that Alex Woodford brought up is that we haven't even got into who pays for the science yet. right? Who pays for it? Where does the money come from? And it's not until you get into academia and professional science that you start to realize how not impartial that is, right? So on the next sort of level up, that changes my, we've called it science with a capital S, right? That changes my perception of what science is all the time. Realizing where the money streams are coming from,
that is something that is always something that should be considered. And I know from my field as well in science communication, some of you may have seen things about the Science Museum and who funds some of their exhibitions. It's something that comes across the whole spectrum of science, which actually, thank you very much, Ben, leads me very nicely into a question actually directly for Alex. From Alex. There's too many Alexes today. So directly for Alex Woodford. So kind of, do you see the themes of the power dynamics into climate science? Oh, I can't even say it. It's too many things. Climate
science. So I'm a social scientist, obviously, and I would say the social world is underpinned by inherently underpinned by power dynamics, and my research is based on the global north and the global south. So there is hugely issues of power dynamics there, and I think it's really important that we as scientists critically assess this and challenge pre-built assumptions about things in order to help create a better world.
Yeah, no, that's some very good points. I'll move on because there's a couple of questions that are actually around a similar theme that actually relates very much to Izzy's talk. But I think I'll probably open it out afterwards. So I think I will go with. I'll go with that one. I may move on to another one as well in a moment. But so I'll direct this to Izzy first, but I'll open it afterwards. Of what is the best advice you'd give to non-scientists when trying to evaluate the validity of the science messages in the public realm?
I think that's a good point. I think it maybe depends on where you're seeing it, but definitely try and find out where the source is, try and see who is spreading that information, if it's coming from kind of a news organization, for example, see if they've credited a certain scientist or a research organization, because that way you'll kind of know, okay, there's been a bit more behind it rather than someone just kind of claiming that this is science. And just try and do a little bit of research really, and maybe it is a good thing to not just take everything as it is and just kind of think for a second, okay, maybe that is not 100% science, even though it seems that I should check this out for a second. So maybe take a step back and delve a little bit more into it.
Yeah. Ben or Al, is there either of you want to anything from kind of your side, particularly on the perspective around the kind of scientific methody side of things? Go Ben first. If you've got
who's going first? Shall I go first? I'll go first.
Ben, you go first.
All right. Yeah. So I think building on what Izzy was saying, the idea of if someone tells you something and you believe it, that's to do with trust more than to do with how we come to find knowledge, right? If someone, a scientist even, tells you that something's true, you trust them unless you've gone and looked into the science yourself. So I think that an understanding of the scientific method as it was described. So in my talk, I had citations in there. So in principle, you could follow back everything I said all the way to years and years and years ago when the first experiments were done around these things, right? So this idea of how the process involved in coming to that knowledge is as important as the final result of it, right? So I think having a healthy respect for that cycle that we were talking about and understanding why that works is almost vitally important to understanding this. Yeah.
Mm-hmm. Al, is there anything you wanted to kind of follow up on that one?
I mean, what Izzy and Ben have already said, I completely agree with. I guess just to add to that, I would say that a big part of science, as I've hopefully made clear, is things changing. And sometimes you see stuff online, you see people with very good intentions saying phrases along the lines of like, I believe in science, which kind of is against the point. to a degree, you have to trust everyone. You can't just be doubting and researching every single new fact that's ever given you, especially nowadays. There's so much going on. I think perhaps a better way to approach it is understanding that the science can legitimately change, and understanding that your views can change, and that's okay. It's not embarrassing or stupid to believe one thing, be presented with new data, and then change your mind on that thing.
Yeah, no, that's a really good point on that one, actually. Let's see. It's kind of on a similar theme, actually, which we'll go to Izzy, and then I'll come to you on this one as well, Alex, actually. But yeah, the science being wrong is a common argument for people, to kind of believe their own opinions based on pseudoscience or outdated science, or just things they read on Facebook. So, kind of from your perspective, let's say, well, Izzy, and then I'll come to you, Alex, kind of what would you kind of think about when you're thinking about tackling a mentality like this?
I think it's really interesting, and I think even from some of my research, there's been like people who've put papers out who said, oh, this person doing X, Y, and Z, that is wrong. And I think it's really interesting, and I think that again, probably just evaluating what is out there. And I think science being wrong is a very kind of stone cold opinion. So again, just kind of consider what is out there, have conversations about science, because science is always changing, and just encourage people to just see what's out there. I don't know if anyone else has got anything to add.
Yeah, well, I was going to come down to Alex on this, because I know obviously you don't necessarily look directly into this, but the science of climate is an area where there is the occasional little bit of pseudoscience getting flung around here and there. But yeah, is there anything kind of your thoughts on things like that?
I agree with Izzy. It's a fascinating sort of phenomenon, and I think the best way to kind of tackle this mentality is to find out what basis these individuals are making or developing their opinions in relation to, and challenging them, and trying to get them to logically reevaluate these ideas, but sort of understanding from their perspective where they're coming from, because I feel like a lot of people, if you come at it with too much aggression, this is true, that is false, it ends up polarizing the issue rather than sort of helping to affect a shift in mentality.
Yeah, and that's definitely something, from my own perspective on the communication side as well. That's definitely things I fully back, and having had some of these conversations with people, I often emphasize, sounds odd, but kindness, because often people aren't like, they will respond better to you being nice about it and not being aggressive, and actually having a conversation about it. You may not change their mind, but that's at least a good way of dealing with it, definitely. And yeah, that's definitely something that I've found. This isn't a question, but it's a really nice quote, so I want to put it up. And also because you spelt O'Brien right. But yeah, science knows it doesn't know everything, otherwise it'd stop. You don't get to fill in the gaps with whatever fairy tale most appeals to you, is a really, really nice way of thinking about it. And that is a really, really nice quote, which is why I wanted to pull it up. I'm going to jump in with a question of my own now, again, because I think it's relevant and also connects to some of the things we have been talking about. And it's so, should all scientists be obligated to share their science in an accessible way outside of their peers? So outside of your immediate group of people you talk to. I know Izzy showed in yours, you had some tweets from soil scientists, for want of a better phrase, which were very much directed at that field. But as you said, social media lets you communicate really widely, as we are doing this evening. We are just on YouTube. But I'll go to we'll go to Ben first on this one. But do you think it should be something that everyone should be doing, all scientists should be doing, or there's some kind of a bit more nuance to something like that?
No, in this case, yeah, I think it's true. There's multiple reasons for that. Number one is because science is funded by taxpayers, so taxpayers should know what's going on, or at least in principle have access to it. Number two, I don't know if you've noticed, but over the last century, science has moved on quite quickly. It's the scientific method is a ridiculously efficient way of getting to the truth, and that allows you to create technologies that are beyond anything you could even think about before it comes around, right? So if people are not aware of what you're doing, that's you can't change society like that without telling people. Do you see what I mean? That's what I'm trying to get at. So yes, absolutely, 100%.
Yeah. Al, is there anything new kind of in kind of your perspective on that?
Yeah, I mean, I especially agree with that second point, really, that science involves everyone nowadays. Some of the names, when I was talking about people like Charles Darwin and Gregor Mendel, they were, Gregor Mendel, he was just a monk living in the middle of nowhere, and he had a garden and he liked doing stuff, and it didn't matter to almost every other person in the world what he did, or at least for hundreds and hundreds of years. Compare that to now, something like the scientists at Oxford developing a vaccine. Every single day, the science they did directly affected the lives, the livelihoods of hundreds of millions of people. We can't just do science and expect people to just believe us because we're scientists and because we're right and we know what we're doing. It's inherent in people's lives, and I think it's one of the things that I think modern scientists are doing a terrible job of, and it's causing a lot of these issues with the spread of fake news, of bad information, of incorrect science, is that real scientists are doing a pretty poor job of it, that we need to really be making a better effort to help everyone understand the stuff that is completely changing their lives on a daily basis.
Yeah, no, I think that is it's a spectacularly good point.
I would come in just a little bit on top of that. And this is just me, and this is not to do with science. This is aside from science. But I would go so far as to say that if you hear that someone is trying to, I don't know, hold knowledge back for some reason, whether that's by not telling you or by even patenting things, if they're hiding information for some reason, it's worth considering why they're doing that. And that's a very political thing, so I'm not going to get very deep into it online. I'm not going to, but it's just worth keeping in mind that patents stop information getting out, so it's worth thinking about them.
Yeah, and there is, and there is actually a live issue at the moment as well around protection of ideas, not just about communicating the science, but it is a conversation around vaccine policy and sharing of patents and opening the patents out. It's part of this, but also beyond this as well. It's not just about sharing. I suppose from my perspective, when I say share, I mean talk about it. Yeah. But also, it's the other side of it. It's the sharing. It's the telling the other people within your field and not keeping it to yourself, which is a really good point. Not what I was meaning when I asked the question, but a very, very good point. That was really nice.
Sorry,
Izzy or Alex, was there anything you were wanting to kind of chip in as well on this one?
I think it's similar to what Al's already said, in the sense that the reason that research is done is to find out answers to questions that will ultimately affect everybody, or at least 1 in 10 of us. And so you're doing that research for a reason. The results should be shared with people who it's going to affect. And I think as well, even within my field of research, for example, there's a need for the sharing of research within that field, and there's the ability to share it. So I don't see why you wouldn't. So I definitely think that scientists should be encouraged to do so, and it's an exciting thing to do. So I really hope that it's done a lot more.
Yeah, and I fully back that one as a science communicator. Alex, was there anything kind of beyond what the others have already contributed? Was there anything you wanted to kind of chip in from your perspective as well, on perhaps coming at it from a slightly different angle?
So within economics, there's a lot of mathematical formalization, which makes my field very inaccessible, and therefore makes it harder to challenge some of these ideas that are now outdated and should be replaced in the current context. So I also concur with what everyone else is saying, that we should be obliged to share our science in an accessible way, in order for it to be challenged to a certain extent.
Yeah, no, I think that is, and that, I suppose that's the other side. It's not just the sharing it. So, as I think it was Ben that you brought it up in terms of a lot of it is funded by the taxpayer. So, the public are paying for it. They should probably get to hear about it. But also, it should be shared so it can be challenged. That's, and I suppose we touched on it a little bit with the cycle of as you're kind of making your observations, and then you're kind of reforming your hypothesis. Part of that as well is it may not be you that does that reinterpretation of data. It could be someone else that does it, because they look at it slightly differently, approach it in a different way, or just spot something you haven't. On a similar subject but slightly lighter side of things, in terms of when it comes to things like film and media, do you think they should consult experts rather than spreading misinformation? So let's go Izzy on this one first up. What do you reckon on this kind of subject?
I think it's interesting because I think to a certain extent, when you're thinking about superpowers and mutants, perhaps that's where the drama comes in and makes it exciting. But I do think that at the same time, there is a kind of responsibility there, because it is perhaps a way, maybe if you don't, you might not even realise, but it might be a way of encouraging what turns into pseudoscience or what turns into fake news and rumours start and things. So I think to a certain extent, have fun with it, but at the same time, it is important to back up what you're saying and make sure it is accurate. Yeah.
Is there any of the other three? Is there something you want to kind of contribute as well on that one? Oh, go on, Al. Yeah.
Well, I sort of think that I think this again sort of illustrates why it's so important for like the average person to be taught, especially younger people at school. We need to do a better job of teaching them this overall understanding of science and the scientific process. Because at the end of the day, it's quite easy a lot of times to watch a film and be like, well, it's a film, it's obviously made up, it's fictional, and for certain things like superheroes, very clearly fictional. But obviously, eventually, we're going to get to a point where it's not so clear, or at least for everyone. And at the end of the day, it'd be ridiculous to suggest that every film about anything remotely scientific has to be completely fact-checked to the last detail. It makes more sense just to have people watching films have a better understanding of science in the real world and an open mind to the ideas put before them. So it's not an issue whether or not the stuff in their media is well researched or not, in my opinion.
Yeah, I should say as well, actually, a lot of films you may not expect do have scientific advisors. Even superhero films have scientific advisors. One of my favorites being Thor. They checked to make sure that the Einstein-Rosen bridge they were mentioning and referencing wasn't wrong. I mean, it's not. Obviously, it's not right. It's not controlled in the real world by Heimdall from Asgard, but the science itself isn't ridiculously wrong. So they do a lot of that checking to make sure it's vaguely right at the very least, which I think is an important point a lot of the time. We're just going to do a couple more because we're almost into the last 5 minutes. So I'll just do one quick one, and then there's a few I want to kind of string together as a final big question. It's just jumped. There it is. So can science always be accurately simplified? And kind of, if not, what do you think is the best way to approach an aspect of science that'd be hard for those outside of the field to understand? Let's go to someone I think probably has one of the more complicated to understand, which is Ben, potentially. And then I might come to Alex afterwards, because I think probably on kind of either sides of the spectrum in some ways, it's kind of can be hard to understand in some ways. But yeah, so Ben, is that something that do you think particularly your area of science is something that can always be accurately simplified?
I spent all day today trying to describe to other scientists what my science is. Sorry. So in principle, And Einstein was one of the people who said this. He said, if you can't explain it to the layperson, you don't understand it well enough. Now, I don't want to disagree with Einstein. I don't. But I'm gonna, because I think you can get to a certain level of maths. I know, right? I think you can get to a certain level of maths that it just becomes like learning another language. And if you haven't put the time in to learn that language, and it's not an easy thing to do, so I could get into general relativity and all this crazy tensor algebra. I'm not going to, but I think metaphor is the way to go with this. And this is someone else in the chat mentioned, where is it? Something about poetry, or it's more of an artistic and creative process. I think describing science through metaphor rather than through hard maths is the way to go about things like that. So I could describe a protein as a protein, or I could describe it as a spring, and it behaves kind of like a spring. Now, you've seen a spring, so you can kind of understand what I'm saying there. It's not really a spring, because it's not, but to a certain extent, I might say it sort of, if you stretch it, it comes back, and we can talk about it there. And it's building up that metaphor is the way to do it, I think.
Yes, I suppose on the kind of the other side of things, of the science side of things, Alex, is that from your side, I know economics can be one of those things that is a little bit confusing to people outside of the field. Do you think on the economic side, is that something that you think can be accurately simplified, or at least explained in a way that is understandable beyond the people within that field?
Yeah, I think I'd essentially echo what Ben was saying. Just making your explanation relatable to everyday instances or items. Yeah, I don't think I really had much. Ben's just done too good a job of answering, I think.
Well, that's fine. I would say from my side as a science communicator, my stock and trade is in slightly odd metaphors and how to explain things in a hopefully understandable way. And it is incredible the science you can explain to even extremely young children if it's broken down and done in a thoughtful way with things they understand and references they know. You can get a lot across to them really, really simply, and they do understand a lot. Now I'm just going to I'll just put it to close. There's one final question that I'm going to get a very short answer from everyone on, but I'm just going to string a couple of comments together to do it. There was Pierre's comment that Ben referenced about it being a creative, critical, error-correcting process. This idea that about the method rather than the verb rather than noun, as Al said. And then there was another one as well from Gary. We teach a lot of science in schools, maybe not enough of the scientific method. But I think actually, Phil, one of the first questions, which I think is possibly the bluntest question we've got, but is the right way to phrase it. Do we teach science wrong? Which is an interesting question. We have only got a couple of minutes left, so I'm going to ask you to all keep it short. But let's go Izzy first, because I don't think we've heard from you in a little while. So as a short answer, do you think, particularly school-wise, do you think we teach science wrong?
I wouldn't say we teach it wrong. I think maybe we just don't include everything that we could, and maybe everything that would be useful. I'll keep it short.
Like that. Al, in terms of what's your kind of opinion on that one?
Well, obviously anything we put in the curriculum means something's got to go out. You know, I'm a scientist, not a teacher, but I do appreciate teachers work very hard and the curriculum is very full. So what I would say is that science should be taught more generally, because ultimately, whether this is primary school, secondary school, really up until sort of sixth form, A levels, you don't need to learn the specifics. You can learn specifics later. There's no point as a young child learning any one specific area of science other than as an example to help you understand the general whole world of science, this scientific method, which then as an adult you can apply to any field of science that you're interested in. And I think that would result in more people being interested in more science. Yeah.
So last couple of short answers. Ben, we'll go to you next. Do we teach science wrong? Yes. Cool. Thank you.
Yes. That's not no. Exams are not good, in my opinion. Yep. That's the end of it. I don't think exams are a good way to measure how good someone is at science. But that's.
Yeah. And to finish up, then, Alex, is there anything kind of you want to add on that? What's your opinion? Do we teach science wrong?
I would concur with Ben. Yeah, we do teach science wrong. I don't think there's enough critical analysis. I think it's a lot of fact memorization rather than consideration of what's going wrong, what we're actually looking at, and how we can apply that in different situations rather than just the one instance to pass an exam.
Yeah, no, from my side, I would probably agree with all of you on that one. Yeah, I think there is more we could do around the scientific method, the creative side. That's something I love, the creative side of science. It isn't a non-creative process at all. It is a really, really creative process, and I think that is something, and it's a process, and that's probably something that can be taught more. But that does bring us to the end of this. So I'm just going to hide that. I'm just going to say thank you, first of all, to the people in the audience. Thank you very much for joining us. There's been some really, really brilliant questions. Thank you to all of our speakers. So Ben, Alex, Al/Alex, and Izzy. There's been some really, really great discussion, and I've thoroughly enjoyed this conversation. Should also say thank you to Abby Connor, who has been behind the scenes working all of the magic and making things appear and us appear and disappear at the appropriate times. She's done an absolutely brilliant job. And you will have also seen her in the comments, Alex Holmes, because she's run this thing for us this year at Leeds, and she's done a fantastic job, and she can now sleep because we are the last one. But on that, I will leave it there and just say thank you very, very much for joining us. We've had a lovely evening, and we hope you have too. Thank you.